Yes, I'm John Hutton, principal at Uzun Case Engineers, and this talk is a case study talk of a project in Chicago. I was the engineer of record. Adrian Prasad is on the line, and he was the project manager. We were both intimately involved start to finish, and this was a project that took start to finish. The project ended up being called Renelle on the River. It is at 403 North Wabash. Let's see. There we go. It ended up at 18 stories, 150,000 square feet. A condominium with 50 residences that go for about $1 million a pop. I didn't get one, but the developer and the CEO for the contractor both have units there now. It was built on top of a 4-story parking deck that was built in 1976. Which was, we'll get very much into that. The developer was Belgravia, BKL was the architect. The general contractor and the concrete contractor was McHugh Construction. So it was nice to have a general contractor that was very interested in the concrete portion of the project. And using a case, we were the structural engineer and the geotechnical engineer, and also they did a lot of the forensic testing was Terracon, and they turned out to be very important in the project. It's a great site. It's very high profile. Next to the Riverwalk in Chicago, directly adjacent to Trump Tower, the big glass structure you see here. This is our project, Renelle on the River. The Wrigley building is just over to the right, and just past that is Michigan Avenue. The air rights had been available for this site for 40 years, but nobody had figured out exactly what you could build on it, and that's what we did. This is the site. All of this was part of the original 1976 construction, which has a 52-story tower, a low-rise, parking underneath all of this. On the left is Wabash. That's a 2-level roadway. So when you look at the site, you see one level coming up above grade. Well, then there's one level that's aligns closely with the upper Wabash, one level with lower Wabash, and one level completely below grade. It was always designed to support future construction, but the drawings were not clear at all as to what that future construction was or how many floors could be supported. And the columns were just sort of evenly, the columns and foundation capacities we found was sort of just evenly distributed over the 24 columns. There did not seem to be any forethought of any particular construction. There was no layout for stairs, elevators, cores. So we. Oh, the other thing to note is the parking spaces in here are all individually owned. They cost about as much as a house, and we were very, very restricted as to what we could do in or around any of these parking spaces, and it had to stay active during construction. The developer did buy a few parking spots in order to get the elevator and stairs in, but very, very few. We had the original drawings, which was fantastic. This is the foundation plan. It's all belled caissons that either bear on the hard pan clay or are embedded into it. As I said, Terracon was the geotechnical engineer, and the great thing about them is that they had purchased the records from a testing agency that no longer exists, STS. So they had all of the original individual caisson installation records. They owned the original borings. So they were very familiar. We did do 3 additional borings, and we were able to increase the bearing capacity. Not a lot, but we went from 25 to 30 KSF for when we're sitting directly on top of the hard pan. And for the ones that are embedded within the hard pan, they went from 30 to 32. This was very helpful because we used 100% of that capacity in a few locations. And we're very close to it in most all of the locations. They predicted the settlement of for the tower that we put on it of 0.6 inches and a differential of 0.4. I would note that only the top portion of the caissons is reinforced. So we had to do an analysis to make sure that we had the right cutoff links for the lateral loads. And I'll get into more to the lateral system in a little bit. So we had drawings, we had good geotechnical information, but we still wanted to verify the condition of the existing concrete structure. And one thing that turned out to be a good thing in this case, it was a little irritating at times, but we had a very nervous developer, and he always approved more testing. He always said, well, if you tested it here, how do you know what it is there? What about this column? Have you looked at that column? So we did a lot of testing, which is great for sleeping at night. We started out with UPV, ultrasonic pulse velocity testing to check the concrete strength as well, it combined with concrete cores. The UPV testing we found very inconsistent and we could not get a good correlation. So we abandoned it and just went to doing more cores. We also did GPR scanning, and you'll see here chipping into the concrete to verify bar sizes and locations. It was very close to what was on the drawings, but yeah, there were definitely a few anomalies. Columns that didn't quite match the size and we had to figure out what the reinforcing was. There's 24 columns, 4 floors. We tested 16 columns on each floor. Every column was tested. I think every column was tested at least twice. We did a statistical analysis. At the time we used 214. I think you could now use 562 in combination with that. we got about a 10% increase in the concrete capacity, but we did have either 2 or 3 columns that were lower strength. And then what we did for those is we would take, and when I say a column, I mean a lift of a column, one floor, one location. So what we did with those is we would do 3 cores in those columns, so we knew exactly what it was, and took them out of the statistical mix. We did test some caissons. They came up, we only did 3 cores for caissons, not really enough to get a statistical average, but we got very good strength. It was designed at 5,000, we got 9,000, but it turned out that actually just using the original 5,000 was enough to develop the bearing capacity, so we didn't have to push it. But it was nice to know the strength was there. So the structural system that we came up with, so we did have a limited height. Somehow they had negotiated a maximum height with the alderman. I'm not sure, as far as not blocking views, and I'm not sure what was involved, but we did have a limited height, but they were trying to squeeze as many floors into that height as possible. Again, with all of the parking spaces owned and utilized underneath the building, we were not permitted to put in any new columns or walls outside of the few spaces that the developer purchased. And it's, the roofs are vegetated. We did end up, we very much were controlling the weight of this to get in the maximum number of floors. So every time the architect would come back with a late decision on whether they wanted to put on terraces or whatever, we had to keep saying, yeah, but you're limited. You can't go more than whatever, I don't remember what it was, 40 pounds a square foot. It was a constant discussion. Okay, again, this portion of the overall existing structure had 24 columns. It had shear walls along Wabash, and on the south side, on the other side of this is where the Trump Tower is. Essentially had shear walls on 3 sides and 24 columns, flat plate with drop panels. So we looked at a steel frame structure. Obviously, you think of it as being light, lightweight composite slabs, braced frames. The challenge with the braced frames is that there were very few places they could go and work with the architecture, and it was not where there was additional consistent strength in the columns and foundations. So we did come up with at least at the concept level of a steel framing solution, but we never pushed it through to figure out how we would reinforce columns and foundations. The floor-to-floor height was 12'4". We got 13 residential levels. Then our concrete option. So it's in a range that you would not think of. We would not typically use moment frames. We would typically be putting in shear walls for a building of this height, but we did not have that ability. So we did come up with a moment frame option, essentially built cores out of moment frames. and tried to keep we kept the structure as light as possible, used 7-inch two-way PT slab. They had a cantilever at one end that we needed to thicken it up to 8 inches. We got the floor to floor height down to 11'8". We got 2 additional floors out of this, and one way we did that is using lightweight concrete on the structure. We didn't use it on every level. We used it on as many levels as we had to get the maximum number of floors in within the height we had. So we used it on the top 11 floors from 8 to 18. So another thing that happened is, so again, the air rights for this were available, but oddly, the air rights on, it is actually the east side, the bottom, what you're seeing here, plan south. The air rights along that line only went to the column center line. Everybody thought that was a mistake. Everybody thought it probably could be fixed, but it would delay the project going through the process of modifying the air rights. And so the architect came back with this fold where they pushed some of the columns west, but that pushed them off of the columns below. So we needed transfer girders. So we needed 4 transfer girders for the air rights. We need 1 transfer girder for a column they just needed to move for interior layout so they could get access to the bathroom, and that column would end up in a closet. We then took these transfer girders and turned them into outriggers because we were still struggling with, even with the moment frames, with too much lateral load going into those 8 interior columns. So we stretched these transfer girders out all the way across the building. This happened at, I think, level 2. And it not only distributed the gravity load better, it distributed the lateral load out to the exterior columns and helped with getting the existing columns and foundations to work. We did do a wind tunnel test. It's a little bit unusual for a building of this height, but again, we were using an unusual floor or a lateral system, and we wanted to make sure we did have the right strength and stiffness. So it had to be, you model it as both a sheltered and an unsheltered configuration, meaning you have to say, well, what would happen if some of these surrounding buildings came down or were no longer there in the future? What would it do to change the wind loads? And interestingly enough, one of the buildings that has disappeared from the unsheltered configuration is the Trump Tower. I don't know that would happen, but it's interesting. So I don't know if you, I'm sure some of you have worked in Chicago, but until recently, Chicago had maintained their own building code that still had a very simplified set of wind pressures. It was simply based on height. There's a table and you pull your pressures out. Very simple, old school. It would be nice if it was this way everywhere, but it's not this way in Chicago anymore either. So they have started out with Chicago defined pressure lateral loads. Oh, and they also at the time did not design for seismic at all. So these are the lateral loads. We did check it per ASC 7. ASC 7 was lower in the narrow direction, larger in the wide direction. But from the wind tunnel test, the loads were smaller in both directions. So we were able to utilize the wind tunnel tests, wind pressures in both directions. We also did do an acceleration comfort test analysis, and our criteria was a peak acceleration for a 10-year return period of 15 millig's, and we came in at 13. But there was a good bit of time on getting us to that point, but it did come in well, and we've heard no complaints. Okay, so the other, as I said, one of the things we did was go to lightweight concrete for the top 11 floors. McHugh, the concrete and contractor, general contractor, had not done this before, so we did a lot of pre-testing on the concrete. The one that was probably most interesting to me was the modulus of elasticity. There was concern about water absorption. There was concern about pumpability. We got some of the lightweight aggregate people involved. Let's see here. Oh, here's the pre-testing that we did. Actually, here's our design mix. We did end up with some silica fume and slag, lightweight coarse aggregate. The strengths came in very well, significantly over the 6,000 psi. The modulus came in like 9% higher, but very close to what was predicted. The density was good. This is what came back, recommendations that we got from the lightweight aggregate producer, saying that it does take a little bit of extra time to dry compared to normal weight concrete, but the main goal is trying to keep it from getting wet over and over and over, and then it dries out relatively quickly. It's been pumped up to 750 feet. It gets pumped for steel structures probably, or composite slabs more often than concrete structures. And McHugh actually did do some trial pumping it on another project of the mix before we got going. And with pre-wetting and other procedures, they did not have any issues with pumping the lightweight concrete. Okay, once we got into construction, we had to deal with a lot of things that weren't quite in agreement with what was on the drawings. The actual location of the existing columns varied. I think the largest one I see on here was like 4.5 inches. So, but they wanted the columns going up to be in exactly the right location. So we did have to go back and analyze the existing columns for all of these eccentricities. And luckily we were still able to get them to work without reinforcing them. Tying into those columns, there's a note on the existing drawings that said that the vertical bars at these particular columns were weldable. So we believe that was their original intent. We did try both, and our intent was that we would either use mechanical or welded couplers. But once they got into it, it was going to take, they were going to have to take out too much concrete of the flat slab in order to get access to either weld them or to turn the screws on the mechanical couplers. And so they came back and they simply wanted to drill an adhesive anchor using standard lap links. So they were very long embedments.
John, you have 1 minute.
Okay, very good. I'm going to, let's see. I would say, okay, we did do settlement monitoring and crack monitoring. It turned out that the settlement was, the actual maximum settlement was 0.4 inches instead of 0.6. So that was good. We used a lot of crack monitors that had been there for a long time, since 2004 when the Trump Tower was put in, and then replaced some. No crack screw more than 0.5 millimeters, so we were pleased with that. And here is the final product. I would point out it's sort of odd. You could see the one picture on the left. You see the entire tower up with no cladding on it. They had a delay in getting, as we're experiencing a lot now, a delay in getting the curtain wall. So we had a little extra time for the concrete to age. And here is the final product.
Wonderful. We do have several questions. Because of time, I think that we could make perhaps one or two. The first question would be, what was the approximate budget for the testing? Since you said so much testing was allowed.
John, this is Adrian. I looked that up while we were, the original proposal was around $50,000, but we did significantly more testing than was in the original proposal. So north of that.
Great, thank you. The other question, it's in the Q&A portion. It says, were there issues with applying roofing materials to a lightweight concrete substrate at the roof, since it takes much longer to dry adequately?
Adrian, you want to answer that? I don't remember any. We did have plenty of time for it to dry, but of course it gets re-wetted all the time.
No, it was not an issue. I do, like you addressed in the slide, there was a lot of debate beforehand, but actually during construction there were no issues.